Yes, welcome back to another a beautiful presentation on control system subject. So today we are going to start lecture number 22, and in today's presentation we will see about mechanical rotational system. Okay, so in this presentation we will see mechanical rotational mechanical rotational system. So in earlier presentations, we have seen mechanical translational system. So in mechanical translational system, we have seen the three basic elements which are very much important and which plays very essential role in finding the transfer function of given transfer function of given mechanical translational system. We have seen that the first element is as mass element m, and then the spring constant k, and the dash part nothing but viscous friction coefficient b, or sometimes that can also be denoted by the letter small f. These are what we have seen in our previous presentations, and we have also solved some examples on mechanical translational system. In the same fashion, today we will see about the mechanical rotational system. It is just similar to the mechanical translational system itself. Only the thing is rotational. Rotational means here the mechanical system is nothing but this is in this will be in rotation in nature. It will rotates basically. It rotates. That's why the name rotational. So here, as we have seen in our previous lectures, here also there are three important basic elements are there in rotational system. Therefore, I will explain you there are three main basic elements which plays very important role in this rotational system in order to find out the transfer function. So the three basic elements, the three basic elements with respect to rotational system means mechanical rotation, sorry, are what are those? The first one is the first one is it is it is movement of inertia. It is movement of inertia, and it is denoted by the letter capital J, is equivalent to the mass element, which is denoted by m in our previous presentation. Here, with respect to the rotational system, the same mass is denoted by its moment of inertia, and that is denoted by the letter J. And second one is, as usual, as your dash part, element, same, it is same as we have seen in previous. And then the third one is it is spring constant. It is called torsional spring constant, or simply you can call it as spring constant. it is again same as your K. Only the thing is the J will differs. Otherwise, the dashpot element B and the spring constant K are same as we have seen in our previous presentations under a mechanical translational system. So therefore, these are the three basic elements that are very important. These are to be considered for this given rotational system. Okay. So and then next one is, so in rotational system, what is the displacement? The displacement. So the displacement is denoted by the displacement, or sometimes this is also called as angular displacement. Sometimes this displacement is also called as angular displacement, that is denoted by the letter theta. The letter theta, that is denoted by theta. Therefore, this is angular displacement. As we have seen in our previous presentation under mechanical translation, the displacement there is either x or sometimes y. So here rotational system, the displacement is theta. And then here the applied force is in the form of torque. The applied force is here. The applied force is here the torque, that is denoted by capital letter T. This is the, whereas in previous presentation means under mechanical translational system it is given as f of t directly. F of t is applied force, whereas in the rotational system the applied force is in terms of the torque T. Therefore, in this rotational system your applied force is in terms of torque, therefore you have to consider your torque as input. Understood? You have to consider your torque as input, whereas the displacement theta as output. Okay, you have to consider torque as input, whereas theta as your output. So then what is the transfer function for this? So the transfer function, basically the objective of this rotational system is also to find out the transfer function for the given for the given rotational system. So now the transfer function, TF is given as, it is again L of t, Laplace transformation of your output by Laplace transformation of your input. This implies Laplace transformation of your output is nothing but theta of t, displacement, and here your input is nothing but your torque T, capital T of t, and this implies we can say it as theta of s by capital T of s. This is what your transfer function. So this is what we need to find out for the given mechanical rotational system. We have to find out this ratio transfer function, whereas in our mechanical translational system it is either x of s by f of s, is it not? X of s means the displacement can be given either x or y or some any other parameter, whatever it is given as per the given problem. Most of the time you will be given as either x or y, therefore x of s by f of s means applied force there, f of t, but in this case theta is the displacement, whereas torque is the applied input force, is it not? This is what the transfer function. Now so we can see, as we have seen in our previous lecture, here also, so we can, here also the same equations will come under the force balance equations. You can write force balance equations, force balance equations for first element is moment of inertia, moment of inertia that is capital J, moment of inertia capital J. So here it is given as your J like this. So this will be given like this. Okay, let us say this is your displacement theta of t, and here up torque, this is the torque is given like this, and then what else is there? Applied torque is there, and this is what? Your J. Therefore what is the force balance equation? Means force balance equation. Force means here force is applied force is your torque actually. So this is your displacement theta. Therefore whenever some torque is applied, this is rotational, and displacement is that, but most of the time it can be represented like this, or sometimes it can also be given as theta of t like that. Okay, theta of t. Sometimes this can also be represented like this. Sometimes they may give like this, or sometimes it rotational basically. Okay, it will comes like this. Actually, this is the correct form of representation. Okay, they will be it will be represented by this. Okay. Now whenever some torque is applied on the physical mechanical body of having moment of inertia J, this J is nothing but equivalent to mass in our previous translational system. Here it is represented J. Therefore, whenever some torque is applied on this body, then this J will also oppose with some equivalent opposite force. That is called, okay, what is that? That is force actually. That is force. F suffix J you can say. F suffix J. Okay. So when some torque, or you can call opposite torque also. Opposite torque also. Is it not? Opposite torque also. As we are applying T, therefore opposite T will be provided by this J. Therefore Tj is proportional to T, means the torque with respect to moment of inertia J. Tj is proportional to, what is that? What is the displacement? D of T, where it is equivalent to d square theta of T by dt square. As we have seen in the same expression, as we have seen in translational system, similar as per the Newton's second law, here instead of d square x by dt square, we have d square theta of t by dt square. Okay. Therefore, this implies if you remove this proportionality, then Tj is equal to, it is capital J, proportionality constant, J into d square theta by dt square, or in bracket you can write theta, nothing wrong in that. So this is what opposing force. This is what the opposing force by J, moment of inertia. Okay, J. Then obviously this Tj is equal to, according to Newton's second law, this Tj is equal to your T. Therefore, this can also be, this also equivalent to T. Therefore, you can write capital T is equal to Tj is equal to, it is capital J into d square theta of T by dt square. Clear? Therefore, this is the Tj is equal to T, that is equal to J into d square theta by dt square. This is the force balance equation for this body, mechanical body of having moment of inertia J. And similarly, let us see for the second element that is a dash pot element. So dash pot, this is for the first element moment of having moment of inertia j. Then see the second one, dash pot. Dash pot. So let us see for the second element, force balance equation for dash pot. Dash pot element. That is nothing but same as we have seen in previous mechanical, translational. Here also it is represented by the letter capital B, or sometimes it may be represented by the capital. Likewise, it may be represented, no problem. And this is your applied torque, and this is your angular displacement. And here in this case, same for the dash pot as we have seen, same rule here also, nothing differs actually. So this is the dash pot element basically. So now the torque opposing by dash pot element TB is proportional to, that is displacement, velocity, that is the theta by dt. Okay, and further this implies if you remove this proportionality, then constant will be kept there. That constant is nothing but your b itself, dash pot element constant b into the theta by dt. You can write, no problem, you can write in bracket theta in terms of t. So this is what your TB means, force opposed by the dash pot element. And finally you can write, according to Newton's second law, our applied torque is equal to the torque opposed by the dash pot element is equal to capital B into d of theta of t by dt. That's all. That's all. Same as we have seen in mechanical translational system. There also we have your f is equal to f of b is equal to b into dx by dt in that case. But whereas instead of x we have theta. That's all. This is for the dash pot element. This is the for dash pot element. And similarly we see for the third element. Understood? So for third element we will see, that is what, spring constant k. For spring element, spring constant, or for spring you can write for spring element. So that is represented by same like this. This is k basically, this is applied torque, this is applied angular displacement, is it not? So from here also your the force opposed by k with respect to applied torque T, that is called as T suffix k, means torque with respect to k, means opposing torque, opposite torque or opposite torque provided by the spring element k is proportional to, what is that, theta of t itself, the displacement only. Theta of k is proportional to this one, and this implies if you remove this proportionality, T suffix k is equal to, it is k into theta of t. Okay. According to Newton's second law, applied torque is equal to the torque provided by the spring element, that is equal to k into theta of t. That's all. This is what the force balance equation. This is the third equation, the third element. Therefore, these are the basic equations or basic information that you should remember while solving the given problem. So therefore, in rotational system we have three basic elements. The first one is the moment of inertia, and the second one is your dash pot element, similar to your mechanical translational system. Similarly, the third one is the spring element. This is also same as in mechanical translational system. So these are the force balance equations we have seen very clearly. So then we will see a simple example on this. We will see one simple example on this, how the differential equation can be written and how thereby the transfer function can be obtained. Okay, let us see one example, very simple example. So here this is the given this is J1, and then this is connected with some spring constant to another mechanical body of having moment of inertia J2, and here you have one dash part element B, and that is connected to some reference. That is connected to some reference. Okay, so this is your K, this is your spring element K, and then this is J1. Here it is given as applied torque T. Okay, here it is given as at this. So before this dash part, it is given as theta, displacement theta. In bracket, it is given as output. It is given as output, whereas here it is given as applied torque. This is applied torque, and then this is K. Okay, so for this, the question is write the differential equations write the differential equations governing to this mechanical system, and second, find out the transfer function is equal to your output. What is that? Theta of S by input T of S. This is what the transfer function. So this is the question. Therefore, find out the differential equation, write the differential equation, and then find out the transfer function. So now we will see the solution part. Go for solution. Let us see the solution. First, as we have seen in previous sessions also, in the same manner we have to draw the free body diagram. We have to draw the free body diagram. Then say for example, here the displacement theta is given. Here nothing is given in the exam, in this problem. Then you can take it as theta 1, no problem. Because J1 it is first, therefore you can J moment of inertia J1, this is the J2. At J2 is giving theta as, therefore whereas at J1 you can write theta 1. Displacement must be there, angular displacement must be there, therefore you can imagine, you can take it as theta 1. Finally, we have to obtain the ratio of theta S by T of S itself. Okay, finally, therefore you can take the displacement with respect to J1 as theta 1, no problem. So now the free body diagram of J1, you can draw the free body diagram. You can draw the free body diagram of J1. J1 means, so same, no problem. It is J1 and we have to represent like this. represent like this, no problem. But here or otherwise representation is not, this weight is not required basically, because already it is there. So just you show here the displacement is theta 1, or otherwise you can draw, because it is, so it is theta of t, I mean theta 1, and applied force is T. This is your, what else is there? K is there basically. K is there. Therefore, okay, K is there. Okay, that you can show, no problem. Either this one or torque, therefore you can show T suffix K. T suffix K. Okay, T suffix K. From here, that's all. Only, so, or T suffix J1 also you can write. T suffix J1, because the moment of inertia itself opposes with some torque, and then the torque applied opposed by this K element. Okay, these are the two basically. However, this is the displacement and it is applied torque. This is the applied torque. Applied torque is there. However, therefore, if you write the expression, what you can write? Basically, I can write directly T is equal to, okay, T is equal to, it is T suffix J1. T suffix J1 is nothing but, this is the torque applied opposed by this J1, plus it is T suffix K. T suffix K, that's all. This is equal to, what is Tj1 actually? What is the torque applied by this? This is nothing but your J1 into d square theta 1 by dt square. Is it not? Your capital T is equal to J1 into d square theta 1 by dt square plus K is the constant, it is spring element, therefore you can write it as theta 1 minus theta. That's all. This is what your differential equation. This equation is called your differential equation. This is your differential equation. And for this, now we need to, this you can call it equation number 1, no problem. For this, you need to apply the Laplace transformation. Okay, then I remove this. So, by applying the Laplace transformation for equation 1, so by applying Laplace transformation to equation 1 means here. So then how it will becomes? It becomes T of S is equal to J1. What is its second derivative? That comes as it is S square into theta 1 of S plus it is K into theta 1 of S minus theta of S. Is it not? Just it will be converted into S form. This is equal to, take theta 1 of S as common, then you will have here J1 into S square plus theta 1 already came outside, you will have only K here. Is it not? So minus theta of S into K. That's all, no? Theta 1 of S we have taken common here. Therefore, theta 1 of S came outside here. Therefore, S square into J or J1 S square plus K will come here, because theta 1 S is already we have taken here. So, what remains there? Minus of means plus into minus, minus itself, theta of S into K. That's what. This is okay. So, this you can call it as equation number 2. This you can call it as equation number 2. Second equation. Okay, now you draw the free body diagram for a J2 and bring the same two expressions will come here also. Then just I will erase this diagram. Okay, so I will write here. So draw the free body diagram. Now the free body diagram of free body diagram of J2. So you can directly write, no problem. You can directly write the expression. Here K is there, I mean common K. Can you able to draw directly? So what it's come here? From the free body diagram, nothing but simply representation of that body and identifying the forces itself. Now you apply your this one. What are the forces acting? The force with respect to K, the force with respect to B. It will come. Then obviously T is equal to what is that? T suffix K, this one, plus similarly T suffix your J2 will be there, no, plus T suffix B, because three elements will come, because dash pot is there, moment of inertia will also oppose spring element, therefore three forces are there, three torques otherwise, torque with respect to K, torque with respect to J2, torque with respect to B, three torques are there. This is equal to, you can write okay, no problem, Tk. If you write Tk first, then it is nothing but K into what you write, theta minus theta 1, because it is common element, no, there is a block here, so here we are considered theta 1, therefore theta minus theta 1. With respect to this one, you consider the displacement first, theta minus theta 1 as this one, plus what is Tj2 is nothing but J2 into d square theta by dt square, plus what is dash pot element? It is B into d theta by dt. This is what your torque equation. Is it not? Then you can remove this also. This diagram is also not required now. Okay. Now this is what your differential equation with respect to, call it as equation number 3. This is what your, I mean, differential equation with respect to moment of inertia J2 of the mechanical body, which is having of moment of inertia J2 with respect to second block, you can say. So this is what the differential equation. Now for this we will apply the Laplace transformation. It is obviously T only. Remember that T only, always in terms of T only, it depends on T itself. Then upon the application of the Laplace transformation, now first equation is also not required now, because we will bring something from this third equation. Okay, after application of the Laplace transformation, then we will substitute that in this equation. Okay, now this can also I will remove, basically this is also not required. Now my interest of equation is this one only, and now if you apply the Laplace transformation to this, for this apply the Laplace transformation, then what you will have, it is T of S, no, T of S is equal to, it is K into what is this, theta of S minus theta 1 of S plus J2, it is second derivative, therefore you will have S square into theta of S plus B into first derivative 1s, you will have theta of S. This implies what we can write, T of S is equal to, you can take as theta of s as common, if you take theta of s as common, then start from second order, I mean s square term, then it is j2 s square plus another theta in b into s, is it not? What is theta? It is k. Here theta of s is there, k. Then minus theta 1 of s into k, is it not? So theta 1 of s and then theta 1 of s, we are separating in this. And now what you will write now? What we will do? And moreover, basically, your if you consider the second one, second we are considering the second block now. There your T of s is not there. Basically, your T of torque is applied on the first block itself, J1. Therefore, on the second one, T is not there. Therefore, this T becomes 0 actually. Here your T is not there, no. Therefore, it is 0 only. Means this we will have 0 torque. Torque is not there. Therefore, it is 0 actually. It is 0 only. That means that what? Theta, this entire thing is equal to theta 1 of s. Understood? Understood? So, it is 0 only because on the second block there is no torque now. That's why you just 0 only. Torque is 0 there. Okay. So, from here what we will do? So, you can substitute, you can get some value for theta 1 of s, that is in terms of theta of s, then that theta 1 of s is substituted here in this expression. Therefore, from this expression what I will write now, you bring the value for theta 1 of s. From this equation, this is the equation, call it as number 4, okay. From this fourth equation, bring the value for theta 1 of s. And that theta 1 of s you should substitute here itself in this place. Then I will remove this one, just I will. So this implies what you will have, this is nothing but theta of s j2 s square plus bs plus k is equal to, means this is minus, you should bring to the left side, na? Then it is theta 1 of s into k, is it not? This implies, so obtain the value for theta 1 of s. Therefore, your theta 1 of s is equal to, so obviously k comes by this total, means theta of s into j2 s square plus bs plus k whole by k will come here. This is what your theta 1 of s. This is what your theta 1 of s. Now substitute this particular theta 1 of s value. Where you have to substitute? Here. Here. Okay. So your theta 1 of s is equal to this, theta 1 of s is equal to this much. So this total entire quantity you substitute here in this expression. Okay. Then what you will have if you substitute that value here, then I will write here this implies theta of s is equal to, what is your theta 1 of s? This theta 1 of s is nothing but this one, theta 1 of s, and that equal to this one, means theta of s into j2 s square, means this entire, plus bs plus k by, it is k is it not? That is what theta 1 of s into, so the product will come basically, that is j1 s square plus k will also come here. It is j1 s square plus k. Okay, is it not? So theta 1 of s, I am substituting this entire here itself. Therefore, j1 s square plus k, this one minus what it will be, the second term is there, that is theta of s into k. This is the second term, is it not? So my problem is over. Then you consider this expression. Here theta of s is there in this quantity, and here also theta of s is there. Take theta of s as common there. Then what you will have? Then I erase this actually. Now I am arriving to the final step. Okay, this implies theta of s is equal to, I take common as theta of s, and from there what you will have? Theta of s, if you take common, then it is j2 s square plus bs plus k multiplied with your j1 s square plus k, both is in product only, by k. In fact, by k is there. Okay, minus means this minus theta of s is already we have taken outside, and you have your k. Okay, clear? Now what we will have? Just to simplify this, and you will get the answer. From this, what we will do? From this, so your theta of s, actually it is t of s is equal to theta of s. Then take LCM, no? Therefore, if you take cross multiplication here, it will come j2 s square bs plus k into j1 s square plus k minus k into k square by k. This implies, and finally, what is our transfer function? Output by theta of s by your applied torque T of s is equal to, so T of theta of s by T of s I have to take T of s by theta of s. If you take the ratio, then it comes to here, then it will become like this, k by what else? j2 s square, it comes like this, bs plus k into j1 s square plus k minus k square. Is it not? This is what your final answer. This is your transfer function. Therefore, this is how we have to find out the transfer function for the given mechanical rotational system. So it is similar to our mechanical translation itself. Okay, so I think you enjoyed this. It is very simple. Therefore, probably you definitely will get in your academic examinations this type of question, as well as in competitive exams like UPSC's engineering service examinations. These two are the very important areas where you will be asked this type of questions. Other than these two, in the remaining all other competitive examinations, possibly you will not get question from this mechanical translational. So you will be asked from block diagram or signal flow graph, and this particular is very important in academics as well as UPSC IAS examinations itself, because the structure of UPSC is something descriptive in nature. That's why. And with this, I would like to, I mean, close today's presentation. I hope that you have enjoyed and you have understood in better way. And I request you all to like this, and if you want to, and please don't forget to share to your friends, and please give your valuable feedbacks and suggestions, so that it will be good for me to improve in subsequent lectures, and thereby every uh, 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 person should be benefited. Okay, so with this I would like to conclude. Thank you one and all.